Okay, so in the previous, so this is Soumen from IIT Kanpur. So this is the lecture 9. So where we will talk about the organic chemistry, some basic principles and techniques. So in the previous class, whatever we have discussed, I will go quickly with the brief discussion of the previous lectures. So the previous lectures was the based on the stereo isomers, and in between in the stereo isomer there are enantiomers. How in the Fisher projection, how it's look like enantiomer, and the enantiomer. If it is the enantiomer, then R and S will be non-superimposable to mirror images. Then only it will be the enantiomer. Okay, not only enantiomer. If we talk about the dust tumor, how the dust tumor will look like. So I have discussed four example A, B, C, D, where A and B are enantiomer to each other. How? Because if you can see the above of where the OH is here, so this is this is a R center. This is also R center. So now the moment you will inject, the moment you will put a mirror to this molecule, so you will get the opposite and the reflection of this molecule. So you will get the opposite isomer of the original isomer. So the R isomer, and when you will go for the nomenclature, not nomenclature, CIP rule, to how to iso how to how can I say, how to say whether it is a which kind of stereoisomers are present there to that carbon. Then we see. So this is the ace molecule. So this is the ace molecule, and this is also ace. So by this conformer, we conclude that so this is RRR. So this is RR, and this is ace. So here it is a enantiomer to each other. Okay. Now C and D, if it is R and if this is carbon is S, then this will be definitely S, and this is R. So that means RS and enantiomer to S are enantiomer to each other. Now, if you see enantiomer and enantiomer, both enantiomers are diastereomer to each other. Okay. Now A is RR, B is SS. So now C is RS and D is SR. So this is the diastereomer to each other. Okay. Now let's say if we now today's class we'll discuss about the conformational. So conformational isomers are the isomers that can be converted into one another by rotation around a single bond. Now, so what they are saying, the conformational isomers are the conformational isomers are the isomers that can be converted into one another by rotation around a single bond. Okay, so let's say, so there are three possibilities. One is eclipse. This is called eclipse, and the second one is called the anti. Okay, and the third one is the gauge. So now, if you see the eclipse isomer is looks like the uh, in the case of eclipse isomer, this is the bond angle between this CH3 and this CH3 is the 60 degree. Then only bond angle. This is called bond angle. So if you see these two same atom or same group, the bond angle is 60 degree. Bond angle is 60 degree. Then it is eclipse. Now the CH3, the same atom or same group, CH3, and here also CH3. If this the same CH3 group is anti to each other, that means the bond angle is 180, 180 degree. Then it is a anti to each other. Now you see there is a two isomer. So where the CH3 and CH3 is the bond angle is the, so if you see this bond angle, so this bond angle is 120 degree. Then it is called the Gauge isomer. 120 degree of the bond angle. So that means, so conformation is for the isomer that can be converted into one another by rotation. So if you want to get first, this is the, let's say, eclipse. Now you go from here. So if you rotate 60 degree rotation by 60 degree rotation, you'll get the gauge isomer. Now another 60 degree rotation, you'll get the anti isomer. Okay. Now let's say from 0 degree to 60 degree rotation, you will get the eclipsed isomer. So this is the 60 eclipsed isomer. Now this is the anti isomer. Now let's say one want to get the go eclipse to anti directly, then one has to go with the 120 degree rotation. 120 degree rotation. 120 degree rotation. If you go with the 120 degree rotation, then you will get the anti. Okay. So this is the conformational isomer. The conformational isomers are the isomers that can be converted into one another by rotation around a single bond. Okay. Now there are three isomers is possible: eclipse, God, and anti. So again I am saying, so eclipse is the 60 degree rotation. By 60 degree rotation, you will get the eclipse isomer. Now if you go with the another 60 degree rotation, then from eclipse to God's isomer, it will be the 120 degree rotation. Now 120 degree rotation, if you go with the another 60 degree rotation, you will get the anti isomer. Now the question is, if you want to, so there are conformational isomers, so three isomers are possible. This is called the eclipse, God, and anti. This is also called the Newman projection. This is actually Newman projection. Okay. Wherever you see this kind of circle molecule, circle, then so this is the what kind of molecule it is? So CH3, H2, H2, CH3. So that means butane. This is the butane molecule. If somebody asks you in butane, butane, in butane, it looks like H3, H2, H2, and H. Okay. Now, if you see CH3, this is CH2, and the back carbon is CH2, and the third one is the last one is the CH3. Now, this is the butane molecule. If someone will ask you, can you draw the butane molecule in perpendicularly Newman projection? Then this is the Newman projection of the butane molecule. Okay. Now, we'll go to the next one, that is the flying wedge or wedge dash projection. Wedge dash projection. So this is called actually flying molecule. So let's say CH4. We know that CH4 is called the methane. Methane. CH4 is the methane molecule. Okay. Now let's say if it is the methane molecule, then methane molecule. If somebody will ask you that, can you draw the flying wedge conformation of the flying wedge manner and flying wedge projection of the methane molecule, then you have to write in this way. So, so total carbon contain total four atoms. So four hydrogen atom is here present. Now two hydrogen atom is in the plane. Let's say this is the carbon at the carbon center. Now another two hydrogen, one is above, another one is the below. So this is the simple molecule of the CH4 molecule. Let's say if we replace one of the hydrogen with chlorine, hydrogen with chlorine. Okay. Now, so let's say this is the A. First, you will identify this is the A molecule H and this is the HB. Why HB? So HB means below and HA means above. So let's say we are actually suppose HA is HA with chlorine. Okay. Now the two hydrogen others will be same, right? So this is the these two hydrogen in the plane. Now the another hydrogen that is the below, the HB is there. Now HA will replace by chlorine. Now see, this is a flying molecule. Now let's say if they ask you, now this molecule, if we from this molecule, so this is not a chiral because the four atoms are different, same. So this is not the chiral. Now I want to replace HB with Br. HB with Br. So now this is below is Br and the above is chlorine. Now this is a hydrogen and this is a hydrogen. Now if I want to replace this this plane. These two hydrogen are in plane, and in this plane, chlorine is the above. So let's say this is a plane. So the chlorine is the above position, and the bromine is the below. Below is bromine. The bromine is like it's like a tetrahedral pyramidal shape. So it's like a pyramidal shape. So let's say this carbon two hydrogen are in the plane. Okay. So let's say this is in the plane. Okay. Now the bromine is below and the chlorine is above. Okay. In this oriented, they are oriented in this way. So chlorine is in the above position and the bromine is in the below position. Now if you want to, so still this is not the chiral. So this is also achiral. This is also achiral. Why I want to get a chiral molecule, a chiral molecule, chiral version of the methane. So this is also a chiral. So this is also chiral. Okay. Now let's say suppose I want to replace these two hydrogen. This is a C and this is a D. Now I want to HC with iodine. Now what I will get? Now I will get the HI which are in the plane, HI in the plane. Now my below is the bromine and the above is the iodine. Sorry, chlorine. Sorry, this is the chlorine. Now this carbon atom, four different atoms present. Now this carbon can act as this carbon. This molecule is the chiral. And what is the? And if you ask what is the chirality of this one, and what is the chirality? What is the R or S? Center. Now this iodine is the most priority molecule because high molecular. So this is the one, and this is the two. Okay, this is the three. This is the four. Okay. Now I want to go with this way. So 1, 3, 4. So 2 is back. So 2 back. So let's say 2 back. 2 back is positive rule. 2 back positive means clockwise. If it is clockwise, then it is R. If it is anti-clockwise, then it is S. Okay. So now, so let's say 2 is back. So 1, 3, 4. So this is anti-clockwise. Okay, anti-clockwise back. That means this molecule is S. So this is matching with this one. So now this molecule is S. So now this is a prochiral molecule. So because this is a chiral and this is a prochiral molecule. So now which one is the prochiral? So this molecule is the prochiral molecule. So we are starting from here. So that's it. This is a prochiral. Okay. So this is the prochiral molecule and this is the chiral molecule. Okay. So now this is the triangle or wedge dash projection, dash projection, flying wedge or wedge dash projection, flying wedge or wedge dash projection, flying wedge or wedge dash projection of the methane molecule. Now we'll go to the Fischer projection. So let's say this is a Fischer projection. Okay, the Fischer projection also one can. So suppose you have this molecule. Okay, suppose you have this molecule and you want to put it in a Fischer projection. Then this is the Fischer projection of this one where the CHO, this is your y-axis or vertical, and this is the horizontal. This is the x-axis. This is the y-axis. Okay. So if you have this kind of molecule, then CHO and CH2OH is the below, CHO is the below, CHO is in the above, and hydrogen is the top, means left side, and O is in the right side. This is the Fischer projection of the molecule. Okay, this molecule, Fischer projection. So now we'll go to the Shaw-Hurst projection. Like in the Newman projection, also we have seen eclipse, gauge, and anti. The same way also the same way the Shaw-Hurst formula also it can be divided in a three way. So one is the eclipse, the second one is the anti, third one is the gauge. So how it looks like. So for the understanding purpose, I the last one The last three example I have taken. One is the black, and the other two is the white. Why? Because we'll then consider the how the black balls looks like black balls and white balls. So the depends on the play placement of the two black ball. We can named them by eclipsed gauge or anti. So now you can see, so these two black ball, one is here, another one is here. These two black balls are switched to each other, means 60-degree rotation. Okay, so this is the eclipse. Now you just go anti to each other. Anti means opposite to each other. Now this black ball and these black balls are anti to each other. That means this is a anti. Now this eclipse to gauge is the 120-degree rotation. So from 120-degree rotation, how? So let's say this one. So this one is, let's say this one, let's say fixed. Okay. So now what will happen? So if you just rotate this one to 60-degree, then what will happen? So this will go here. So let's say 60-degree. Okay. This is a, let's say, 60-degree rotation. Okay. So let me draw this one first. This one. So this is the eclipse. Now let's say this one will go first here, 60-degree, 60-degree rotation. Okay. Let's say this one is fixed. This whole thing is fixed. This whole thing is fixed. I am fixing this position. Now I am rotating this part. Okay. So then this will go 60-degree. This will also go 60-degree. So then what will happen? So you will get, what will get? So this part is fixed. This is a black. Okay. This is a black. Now this is a white, and this is also white. Okay. Now the black one will go to the middle center. Why? You are rotating this one. Now see, this is, so this one will go here, this one will go here, and this one will go come to here. So now this black ball will come to this white ball position. This white will come to this place, and this ball will go to the black ball. So now this is a black ball, and this is a white ball. Sorry, this is a white ball, this is a white ball, and this is a black ball. Now what we are getting by 60-degree rotation? What we are getting by 60-degree rotation? We are getting the gauge isomer from. Okay. Now let's say, but the bond angle between here is the 120-degree. So this is the 120-degree. This is 60-degree. This is 60-degree bond angle. Okay. This is 60-degree. But this is 120-degree. Why 120-degree? Already it was 60-degree was present here. But again you are rotating 60-degree. Then you are getting a 120-degree, total 120-degree. So this is a gauge. So that's why in gauge conformer, so you will have a 120-degree bond angle. Then you want to, let's say I want to get the another 60-degree rotation. Okay. Now let's say this part also fixed. This is fixed. I don't want to rotate. I don't want to touch this part. But I want to touch this part. I want to go for this one. Now 60-degree. So this one, another 60-degree rotation, it will go here. And this one will go to middle one. And this one will come here. Okay. Let's see how it looks like. So now we have this one. Black ball is above. Okay. Now the white two ball is here. Okay. Now it will come. So another. So now this black ball will come to this position. This white ball will come to that white ball position. Okay. So now this is the black ball. Now it is after 60-degree. It will come here. Then another 60-degree. This white ball, and then here white ball. Okay. Now you can see this is the anti to each other. Now this is a anti to each other. This is the anti-isomer. Now we got this one. So how it looks like, and if somebody asks you what is the compound, this is, so this is, you can see CH3 and CH3. Let's say I am talking about the only CH3 CH3, but if it is a different atom, then it is a different case, that how we can consider how the rotation will looks like, how the anti-conformer looks like, and how the gauge conformers looks like. So it depends. Okay, we'll not go to that part of now in this moment, but here I can tell that, but here I can tell that the if we start from the eclipse isomer, then upon 60-degree rotation, you will get the gauge isomer. Then again another 60-degree rotation, you will get the anti-isomer. So, but the bond angle between this one to this one is the total is the 120 degree, because it was initially was the 60 degree. But by rotating of the 60 degree, you will get the gauge isomer. Okay, so we don't want to go further on the in the basis of what can I say? So that is much depth of the this one. So this is one example is enough for the Shohorst formula, how the Shohorst formula it looks like. Okay, now plane of symmetry, light. Okay, you can see this molecule is the chiral light. How this is the chiral or not? So if this molecule is the, if somebody will ask you the whole molecule is chiral or not, so there are two possibilities. One is the plane of symmetry and another one is the central chirality. So although this whole molecule has a central chirality, how central chirality? When central chirality will comes out. So here you can see two chiral center, right? Two chiral center is here because why? This carbon contain one hydrogen atom, one OH atom, one CH3 atom, and one this bigger group. So total four different atom one carbon atom content. So that means it should be chiral. Okay, this is chiral actually. This is actually chiral. So let's see. We'll count the what is whether it is R or S. So let's say this is a one, and this is, let's say CH. So this will be two, and this will be three. This is four. As I said yesterday in the previous class, if in the four the least priority is in the x-axis, then it will be positive rule. So positive rules means, so one, two, three. That is clockwise. Clockwise means, let's say this is a R. Okay. Now let's say the same way. One, this is a two, this is three, and this is a four. Now one, two, 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 three. So let's say one, two, 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 three. Anti-clockwise means S. So now you can see. So R, if you pass a plane here, if you pass the plane from this carbon and this carbon, so let's say this is a plane. Okay, now you just see the mirror image of this one, because R will always give the S isomer, the opposite one. Okay, and even if you pass a plane from here, this whole molecule, it is just a equal. It not equal means the identical or same structure. So that means although the whole molecule has a two chiral center, one above one is the R and the below one is the A, but still this molecule is not optically active, optically inactive. Why? Because if the molecule contains any symmetry of the molecule, that is plane of symmetry. So this is called plane of symmetry means this is called sigma. This is called sigma. So maybe in a higher class you will learn all these things, but I will just touch this kind of small thing, so that you'll have an idea about this. Maybe this is as it is 11th class, but I think this is, we also read this kind of thing in the BSc level, but now this is all this syllabus up to the 11th. So it's better to have a small idea, a little bit idea about what is plane of symmetry, what about the things, spiral center, optically active, optically inactive. So this kind of question maybe in your normal examination center it will not come maybe, but it will come maybe in NEET exam or joint entrance exam. So medical. So this kind of exam, maybe you have to face this kind of problem. So that's why it's better to know. So so you can see if they have the last plane of symmetry is there or not. If you pass a plane, you can see the just identical structure of another one. So the whole molecule is optically inactive. Okay, this is called planar symmetry. Now, the another interesting point is the center of symmetry. How the center of symmetry looks like. Okay, so let me first draw this one. This is really interesting. I really got much more interested on this kind of problem. So how it looks like. I also like this kind of problem. So maybe you will have an idea that how it looks like. Okay. So let's say this is a hydrogen molecule, this is a hydrogen atom, this is a CH3, and this is a C double O, and this is a hydrogen. Okay. And this is a hydrogen. This is also hydrogen, and this is actually CH3 molecule. And this one is C double O A. Okay. Now you see this CH3. If this is the center of carbon it is here. Let's say this is a whole molecule. Now we just imagine this the whole molecule in this way. So let's say this is a CH3 molecule. If we pass a plane from here, and now it is going and inject the plane, and it is also touching to the this CH3. Okay. And the same way, if it is a C double H group is here, now it is also passing through this center of symmetry. Then it is also going to touch to the another C double H. Okay. Now this hydrogen and this below hydrogen and this above hydrogen. Okay. Now it will also go in this way, and here one hydrogen is above, one hydrogen is below. Now let's say this one will go. Always we have to see the opposite isomers. Okay. So now let's say here also it is going and touching here. So now this is going through a center. So that means it has a symmetry, and this is called the center of symmetry. Okay. This is called the center of symmetry. So the previous one is the sigma, center of plane of symmetry, but this one is the center of symmetry. Okay. So we have discussed center of symmetry, plane of symmetry. Then what we have discussed? Newman projection. So these are the important points in stereochemistry. If you have an idea about this one, so then you will not have any problem in the stereochemistry part. Any kind of question you can solve easily. Okay. So this is also another important thing. Now we can now there is another terminology that is called regiochemistry and stereochemistry. What is the regiochemistry and what is stereochemistry? Still, we are discussing about the last one or two class. We are discussing about the stereoisomer, stereochemistry, all these things. But regioisomer or regiochemistry we never discuss. So the stereochemistry determines how the stereoisomers are arranged. The stereochemistry, the stereochemistry actually determines how the stereoisomers are arranged. Okay. So first we have to know what is the stereochemistry and what is regiochemistry. Then we will come to the difference between the regiochemistry and stereochemistry. So stereochemistry determines how stereoisomers are arranged. The main difference between the regiochemistry and so as we all know that the stereochemistry depends on the arrangement, the spatial arrangement of a molecule or an atom, of an atoms or molecules or a group in a spatial arrangement. The molecule, how the spatial arrangement of a molecule in a space. Sorry, the spatial arrangement of a molecule or atom. This is called the stereochemistry or stereoisomers are arranged. How the spatial arrangement. It's always talked about the stereochemistry. We always talk about the in stereochemistry or stereoisomers are always talked about the spatial arrangement of a molecule or of an atom or of a group, not the 2D isomer, not the 2D manner. We always talk about the 3D isomer. The main difference between the regiochemistry and the stereochemistry is that regiochemistry represents the atomic structure of the regiochemistry represents the regiochemistry represents the atomic structure of the ultimate product of a chemical process, whereas the stereochemistry explains the atomic arrangement and the modification of the molecules. So the regiochemistry represents the atomic structure of the ultimate product of a chemical process, whereas the stereochemistry explains the atomic arrangement, the spatial arrangement, and the modification of the molecule. Okay, now we'll come to the some of the question answer session. So maybe so this is almost going to finish this part. So then I will discuss here some of the question here. I have taken some of the question from some Wikipedia and also some books, textbook. So I'll discuss these things. Okay, this is not the new question. It is already available in internet and Wikipedia also. Some of the other books also I have taken from there. So you can see that the simple example of this one. So assign the I have taken one simple example where bromine, CHF and CF3 is there. So assign the R or AS to the indicated center in the feature projection. Now you can see here. Okay, so this is a one because in the case of this one, this is a one. Okay, so this is a one, and this will be fluorine and CF3. Okay, in the case of fluorine and CF3, fluorine will be more compared to carbon because fluorine is 9, carbon is 7, it's 6. Okay, now let's say this is a 2, now this is a 3, now this is a 4. Okay, now 1 to 2 to 3. Okay, 1 to 2 to 3. Okay, this is a R. Why R? Because clockwise this is R. So y axis least priority, positive rule, positive rule, and negative rule. Negative rule is the negative rule is and the anti-clockwise will be S and this will be R. Clockwise will be R. Okay. Now Fisher projection. This is called Fisher projection. So I'll go quickly and so that we can finish it quickly. So the second question is the assign the R or S to the indicated center. This Sauer's projection. So this is also Sauer's like projection. Okay. Now we have to identify the center. Yeah. So this is your one. This is two. This is this carbon is attached to another carbon. This carbon then again. So this will be two. Why? Because this carbon has oxygen, but this carbon has bromine. So this is two. This is let's say three, and this is let's say four. Now 1 to 2 to 3. So this is a clockwise. So that means this center is R. Okay. Now let's say this center. Okay, this is a 1. Okay, this is a 2. This is a 3. This is a 4. This is again. This is a clockwise. So that means this is also R. Okay. So now this is also important. So this Sauer's projection we have discussed. So this is also so one we have discussed in the Fisher projection where it is whether it is R or S. Now here we have discussed the Sauer's projection. This is also done. Now we'll discuss the one. So total three way we have discussed. So one is the first one is the Fisher one. Second one is the Sauer, and the third one is the Newman projection. So Newman projection how it is if it is R or S we need to see. Okay. So how we will see whether it is R or S. This carbon center. So let's say this hydrogen and hydrogen are in a opposite direction. Okay. So let's say this hydrogen. Now hydrogen is done. Now OH is here and Br is here. Okay. Now CH3 CH as both are same. So one hydrogen is common. The CH3 whether you will write here, whether you will write here doesn't matter. So let's say CH3 here and here also CH3. Now you can see this is bromine 1, this is OH, this is 2, this is 3, and this is 4. So now 1, 2, 3. This is clockwise. So this is clockwise, that means R. Okay. Now what we have learned. So in y-axis, if it is y-axis, least atom is present and positive rule. Okay, and the x-axis least atom, that means negative rule. Okay, negative rule means positive rule means clockwise, means R, in the negative, in the anti-clockwise, that means S. The negative rule, when it is negative rule clockwise, that means S. Anti-clockwise, that means R. Okay. Now we have discussed, one is Newman projection, another one is the Shaw's projection, and the Fisher projection. So total 3 questions we have done. Now which one is the achiral molecule? Okay. So now you can see, actually, if you see the molecule here, no, if you see the molecule here, so which one is achiral actually? So if you pass a plane of symmetry here, this is also plane of symmetry. If you see, if you pass a plane from here, you can see the identical. So this part is identical to each other. So this is not chiral. If the plane of symmetry is there, then this is a not optically not active. Optically not active means achiral. So they are asking about the chiral, right? So this is not a chiral molecule. Now they are asking whether it is chiral or not. So these three, this CH3 is opposite the actually this CH3 and this CH3, then hydrogen, hydrogen, and chlorine, chlorine, anti to each other. Okay. So now let's say draw this one, chlorine. Sorry. So this is chiral because why? So this center is chiral. Why? Because this carbon has this much bigger group, and this carbon has CH3, this carbon CH2CO, another 4. So that means this is a chiral. So this center is, this is a chiral. Now we have to see whether it is chiral or not. This center is this P atom is chiral or not. Let's say draw in a Fisher projection. Chlorine and chlorine. Okay. Now in the chlorine, first chlorine, what will happen? So just rotate this one, chlorine. If I rotate this one in this way to better imagination, so let's say chlorine will come here, CH3 will come here, hydrogen will come here. Now CH3 will come here. Now this hydrogen will come here. The 60-degree rotation. Now Cl will come here. Now another opposite, all these things are same. Okay, now 60-degree rotation, that means Cl will also come here. This one will also come here. Cl will come here. Hydrogen will go there, and the CH3 will come here. Now see, this is the CH3. Let's say CH3 right side. Right side I am writing here also this one. So let's say top one. Top one will count. First take the top one. The CH3 is here, hydrogen is here. Now let's say another one. Whether it is the Cl is here and the CH3, if which one is the right side, so it will come here, and the hydrogen is will come here. Now see, is there any plane of symmetry? No, right? Because if you pass a plane also, it is not the same. But in case if you have this kind of molecule, so this is called trio molecule. This is not eride trio. This is called trio. What is eride trio? This is CH3. This is CH3. This is hydrogen. Okay. Now let's say this is also CH3, and this is hydrogen, and this is chlorine. Now you pass a plane from here. So this is now eride trio. This is called eride trio. Now this is not optically inactive. This is achiral. Optically inactive. This is optically inactive. Okay. So now we are done. So the A1 is the achiral, A is achiral, this one is chiral, and this one is also chiral. Okay. Now we'll go to the, so we don't have any other things. So maybe we'll stop it here, and maybe the next class, in the next class or whatever we have discussed. So you can see, so this is also done, and Newman projection, Fisher projection, and Schauer's projection. So I'll go through quickly, as it is almost, this chapter is almost completed. So I'll go through quickly from the beginning, whatever we have discussed today. So first we have discussed the conformational isomer. So conformational isomers is, what is conformational isomer? The isomer which can be converted to into one another by just rotation around a single bond. Okay, then only we can um, by rotation of a single bond, then we can get this molecule. Then we can get the conformational isomer. So now, if you want to get, the first, so there are three possibilities. One is the eclipsed isomer. The second one is the gauge isomer, and the last one is the anti-isomer. Okay, so eclipsed isomer is the 60 degree. By 60-degree rotation, you will get the eclipse to gauge isomer. It is total 120-degree bond angle. By another 60-degree rotation, you will get the anti-isomer. So this is the conformational isomer. Now let's say we'll go to the second one, which is the Sawhorse projection. The Sawhorse projection flying wedge is what? So flying wedge is the CH4, that is methane. So CH. So two hydrogen are in the plane, and another two hydrogen are not in the plane. So that is one is the above, and another hydrogen is the in below. Okay. So now, but if we want to get a CH4 as a chiral molecule, we have to go through in this process, and where we are getting so three hydrogen, if we replace with the chlorine, bromine, and iodine, then we can get the chiral version of the methane molecule. Now, this is the prochiral molecule of this CH4. Okay. Now you can see here Fischer projection. Now, if it is a Fischer projection, so if it is a Fischer projection, then CHO and CHO and CH2OH. So this is a Fischer projection of this molecule. Now the Sawhorse formula is the Sawhorse formula also three types. So what are the three types? So one is eclipse, another one is the anti, and third one is the gauge. So from eclipse to gauge is the 60-degree rotation, and again another 60-degree rotation. By total 180-degree rotation, they will get the anti-isomer. Okay, this is called the anti-isomer. Now, so let's say anti-isomer. Now it is a planar symmetry. So what is planar symmetry? So let's say although you have a suppose one molecule you have, so but if the molecule has also two chiral center, but still this molecule has a planar symmetry, then it should not be a chiral molecule. It will be optically inactive molecule. That means a chiral molecule. So now the center of symmetry. So let's say this is a good interesting example where the two C double H the anti to each other and going through a center. So and also CH3 to CH3 also going through a center. So this is called the central symmetry. So that means if this kind of molecule is there, although they are looking like their chiral center is there already, but still they are not chiral. Why? They are not chiral because they have the central symmetry. Now the regiochemistry and the stereochemistry. So what is the difference between regiochemistry? So regiochemistry, atomic structure of the ultimate product of a chemical process. So the regiochemistry represents the atomic structure of the ultimate product of a chemical process. So whereas the stereochemistry explains the atomic and arrangement and modification of the molecule. Stereochemistry explains the spatial arrangement and the modification of the molecule. But the regiochemistry represents the atomic structure of the ultimate product of a chemical process. And the if you see anywhere the Fischer projection, how to know whether it is a whether it is a Fischer projection, and Fischer projection it is R or S. So it's the easiest way if you see anywhere. So x-axis and y-axis. If the x-axis, if it is the x-axis, if in the x-axis, in the x-axis, x-axis is the least priority, or in the x-axis, then it is a negative rule. Negative rule means the clockwise it is a S, and the anti-clockwise it is a R. Now 4 it is a y-axis barabar. If it is in the y-axis barabar, then it is a positive rule. It will follow the positive rule. Now let's say if it is a going the clockwise rotation, then it is a R. And if it is going to an anti-clockwise rotation, then it is a S molecule. So now let's say here, so bromine is 1, fluorine is 2, and the CF3 is 3, and the hydrogen is 4. So now 1, 2, 3 clockwise, and the clockwise rotation positive rule, that means R. The molecule is whole molecule is the R. Done. Now the Sawhorse projection. Sawhorse projection. Sawhorse projection, two center is there. So you can see one OH is there at the second position. So which one will be the second? Because the here, although it has a COOH group, but here CHFBr, but here COOH, but here fluorine also there, bromine also there. That's why this is 2, this is 3, and the 4 is the hydrogen. Now this is 1, 2, 3. So this is also going 1, 2, 3. This is clockwise. That means this center is R. R. Okay. Now let's say this is 1 and this is 2. And now this is 3. This is 4. Now also it is going via 1, 2, 3. Okay. 1. Okay. No. So 1, 2, 3. Okay. So but here it will be 2. Why 2? Because carbon is directly attached to fluorine. But here carbon is directly attached to carbon. Right. So that's why we go with this one. So this is, if it is 1, this is fluorine is 2, this is 3, and hydrogen is 4. So that means 1, 2, 3 in this way. So that is also clockwise. That means this is also R. And the Newman also, you can see Newman. So in this case, the back carbon has the 2CH3 is the same 2CH3. That means same molecule. That means the back carbon is not chiral. Only the this one is the chiral center. So now you can see. So it is 1, it is 2, it is 3, and it is 4. Okay. Now you just count it 1, 2, 3 clockwise. That means R. Okay. Now they are asking 3 examples they have given, where they are asking whether it is the 3 molecule, which one is the achiral. So the first one, you can see, if you pass a plane here, so you can see this is the achiral molecule. This is almost identical. But in this Newman projection, if you just rotate this one, you will get this molecule. By 60-degree rotation, you just rotate the 60-degree. So the 60-degree rotation, fluorine will come here, CH3 will come here, and hydrogen will go here. The same way, this CH3 will go in that position, Cl will come in this position, and the hydrogen will go in that position. So like same way, I have also drawn here. I have drawn here. I have also drawn here, and now you can see the chlorine CH3 hydrogen. Chlorine CH3 hydrogen. Which one will be which side? Then we have to push it in the that side only. Now let's say this one. The back carbon, which one is the right side? It will be always in the left side. Okay. So this one I will tell you how to do. Maybe 1 or 2, 1 plus I extra I will take for that purpose. Where how you can convert from Newman to Fisher projection or Fisher to zigzag projection. Okay. That I need to take another 1 class, but I'll not go here. Then you will get the 3 over. But if you pass a plane from this carbon center, but there is no such same identical molecule. So that means this is not the chiral molecule. This is the chiral molecule, right? This is not the achiral molecule. In the same way, this is also central chirality is there. But if you pass a plane here, so there are no such possibility. Or if you pass a plane here, so there is, although these 2 carbon is here, but 1 carbon is attached with the another CH3. So that means this carbon is not also. So this molecule is not also achiral. This is a chiral molecule. Okay. Now it is almost finished. Okay. Thank you. And thank you, sir, for giving me this opportunity to finish this project, finish this chapter today. And I'll bring some new chapter. Okay, and some extra things left. So maybe I will take another 1 class for this one, and also I'll start a next new chapter for this thing. Thank you, sir.